All right, so now I'm going to look at question 3. So I want to actually apply Green's theorem to be able to do the vector calculus stuff that I want to be able to do. Okay, so Green's theorem, we want to show the following. We want to show that if I'm looking at the integral along the boundary of an omega, or a domain omega, that this is equal to what's happening over the interior of the divergence of the vector field. Okay, so let me just point out, you might remember from your calculus class how the divergence of f kind of, if f was of a vector field, the divergence kind of was how much f is spreading out. And this is one of the reasons. This identity is going to be one of the reasons. Because what's happening here, as we mentioned before, if I have something like this, what does this represent? Well, if f is flux, if I look at this point here, and f is flux, f dotted with n times n, this right here is going to be the component of flux that is perpendicular to the boundary. And so that is the component of flux that is bringing the quantity, whatever we're looking at, that is the component of flux that's bringing the quantity out of the domain. That's going to be important for the next problem. This is the component that's bringing the flux out of the domain. And so now, if we're adding all of this up, that's what the integral is. We're adding up all of these components around the boundary. What we're saying is that this right here is how much is flowing out of the domain. So this quantity is how much is flowing out of the domain at any time. F depends on x, y, and t. And now we're saying that we can rewrite it in this form here, involving the divergence. Okay, so why can we do this? Well, I'm going to erase this in a minute. So f, I'm going to say the components of f are p and q. Okay, and let's say the boundary of omega, has parameterization r of t equals x of t, y of t. And so what this means is that the tangent vector, I'm just going to write it as t, the tangent vector is going to be equal to x dot of t, y dot of t, divided by, and I'm just going to write it like this, r prime of t. The magnitude of r prime is this vector, so I'm dividing by its magnitude to get a normal vector, or a unit vector. And what is n? Well, n, we saw before, n is going to be equal to y dot of t minus x dot of t, and then the magnitude of these two vectors are going to be the same. So to get a unit vector, I'm going to divide that. Okay, so let's get to work then. So if I want to compute this vector here, how do I compute that? Or if I want to compute that integral, how do I compute that integral? Okay, so now f dotted with n, so let's think about this. F dotted with n, f is pq, this is my n vector here. So, well, let me actually do one intermediate step. So let me just write, it's going to be f dotted with n. Okay, so if I have a parameterization of the boundary that goes from a to b, like this is the parameterization of the boundary here, going from a to b, I didn't write it there, then this is going to be f of x of t, y of t, dotted with n x of t, y of t, times the magnitude of the vector. Okay, this is just the normal line integral formula. Okay, so this, how does this work out? We're going to have a to b. Okay, the f component, or sorry, the x component, I'm doing a dot product here. The x component of f is p. I'm just going to write this as p without the argument. Okay, now I'm dotting it with the x component of n. So the x component of n is y dot over the magnitude. So this is going to be times y dot over the magnitude. Okay, now I'm going to add the y component of f multiplied by the y component of n. So this is going to be minus q x dot over the magnitude. And then I'm multiplying by this magnitude. Okay, so I'm going to just leave this here, but make this cancellation. Notice the r primes here cancel with the magnitude there. And so what we're left with is the following. We're left with p y dot minus q x dot dt. Okay, well, what is this equal to? This is exactly the integral over the boundary of p dy minus q dx. And by the previous question, I know that by Green's theorem, this is equal to the boundary over omega of the x derivative of p plus the y derivative of q. But notice what we're doing here. It's like the x derivative of p times the y derivative, or plus the y derivative of q. So this suggests this notation, the gradient dotted with the vector field. So what does this mean? I'm saying here the gradient, I'm thinking about the gradient as being a vector of differential operators like this. And so when you do the gradient dotted with f, you're going to have the x derivative, or sorry, the x component of the gradient applied to the x component of f. So that's going to be like times, times, but we mean do the operator. The x derivative, so it'll be like this, and then plus the y derivative times q. And so what we get is this is going to be equal to the integral over omega of the divergence of f dA. Just like this. Okay, and this is what we wanted to show. Well, this is the first thing that we wanted to show. The second thing that we wanted to show is what happens if f is equal to the gradient of u. So what happens if f is equal to the gradient of u? So as I'm erasing, why would we care about that? Well, remember that according to Fick's law, if a quantity is diffusing, and that is it's obeying Fick's law, then its gradient is going to be proportional to flux, or flux is going to be proportional to gradient. The flux of an item is going to be proportional to the gradient. Okay, so if I'm looking at something like this, the gradient of u dotted with n, the other notation for this is the normal component of u around the boundary. This is how much is flowing out of the boundary, or out of the domain through the boundary. Then if I apply this theorem, Green's theorem, or the divergence theorem here, I guess is what this is called, this is going to be the integral over omega, gradient dotted, now f is the gradient of u, dotted with the gradient of u dA. So let's think a little bit about what this is. So the gradient dotted with the gradient. Okay, so the outer gradient is going to be this partial derivative operator. And now we're dotting with the gradient of u, which is just the x derivative of u, the y derivative of u. And when we do this dot product, again, interpreting multiplication as doing an operator, this is going to be equal to the x derivative of the x derivative of u, so just the double x derivative of u, plus the double y derivative of u. It's going to be the double x derivative of u plus the double y derivative of u. And this has a special name. It's called the Laplacian of u. So we're going to have this triangle with the point on top. And so this is equal to the integral over omega of the Laplacian of u dA. Okay, so what this lets us do is it lets us connect the flux. So this is important. What this lets us do is it lets us connect the flux of u around the boundary. In other words, how u is changing, or how much is flowing out of the boundary, how much of u is flowing out of the boundary, to the Laplacian of u over the interior of the boundary. Okay, and this is going to be important later on as we do mathematical things. Okay.